right, so let's go through this application exercise. So to start off with, you're going to open RStudio Pro, create a new project, click File, New File, R Markdown. And so from this, you're starting from the template that RStudio gives you here, which is the same thing you did last time, but we were just putting in math, and this time we're going to be putting in some code. And so you delete everything except for this untitled output HTML. If you notice here at the top, I can actually also add an author line so that I can put myself in as the author. So that's what I've done here. And then give your work a sensible title, and when you've finished, go ahead and knit it and upload to Canvas. Okay, so the first question asks us to fit a linear model using the MT cars data frame predicting miles per gallon from weight. And so I'm going to do that. And so the MT cars data actually comes with the with R. So when you install R, that automatically comes with it. The first thing I want to do before I do any kind of adding, fitting any models, is I'm going to want to make sure I have all my libraries loaded. And so I'm going to call this chunk load packages. And to make these chunks, you put the 3 tick marks, open curly bracket, and close curly bracket. Make sure you've got the letter R there, and then a unique title here for the chunk title. Okay, so I'm going to load the tidy verse package and the tidy models package. For the most part, these are going to be the ones that you always want to load at the top of your file, but sometimes we're going to have additional packages to get data, like you've seen in the labs. Okay, so I load those, and now let's fit a linear model using MT cars to predict miles per gallon from weight. Okay, so we start out with the linear reg function. We have to set our engine. We're going to use LM here. And then we need to fit a model. I'm going to fit where the outcome is miles per gallon and the predictor is weight. And the data here is MT cars. Okay, great. So there's our model. And now this next question asks me to pull out the coefficients and confidence intervals using the tidy function and then interpret them. So I'm going to save this output here. I'm going to save this as LM MT cars, so I can remember this is my MT cars linear model. And so for this next question, I'm going to fit it. I'm going to make another chunk. Now you can also, there's a keyboard shortcut to insert a chunk. If you do Command, Option, and the letter I, it'll create that little chunk for you. Okay, so now I'm going to use my LM_MT cars object, and I'm going to pipe it to the tidy function. So this is going to be the output from LM, so I'm going to label my chunk accordingly. Now if I just run this, I end up with my coefficients, my standard errors, my t-statistic, and my p-value. But the question also asks for confidence intervals. And so if you remember, there's an argument conf.int equals true. And when I do that, I get my confidence interval. So you'll see this conf.low and conf.high. Okay, so now I'm asked to interpret these. So we're going to interpret them for both the beta 0 and for the beta 1 for weight. And so the intercept is 37.3, the confidence interval of 33.5 to 41.1. When weight is 0, the expected value for miles per gallon is 37.3. So that's what we mean by our intercept, that the expectation or the average y value we would expect is 37.3. Okay, now I'm going to interpret this next beta coefficient. And so the coefficient for weight, so it's important to mention the actual x value here. Some folks in the lab and things were just putting x, but you want to say the one that you're talking about. So the coefficient for weight is -5.3 95% confidence interval, negative 6.5 is the lower bound, and negative 4.2 is the upper bound. A 1 unit increase in weight yields an expected increase in decrease, let's just say change, in miles per gallon of negative 5.3. Now, because this is just simple linear regression, we have no other variables in this model, we don't have to say holding all other variables constant. But if we had another variable in the model, we would have to say that. That's very important. Okay, so now we've interpreted that beta coefficient. Let's interpret this confidence interval, because this actually, it seems like a lot of people were getting tripped up on interpreting confidence intervals on the last assessment. So I just want to make sure that we're all on the same page here. And so when you interpret a confidence interval, this is interpreted as if we were to do a similar sampling procedure multiple times, and each time we calculated a confidence interval, the true coefficient for weight would fall within the calculated confidence intervals, so I've got an S there, intervals, 95% of the time. So I'm going to write that out. If we were to repeat the sampling procedure many times, we would expect the true coefficient for weight to fall within the intervals calculated 95% of the time. This is different. This is not the same as saying the true coefficient for weight is within negative 6.5 to negative 4.2. That is not correct. And it's a tricky concept, but every time you were to repeat this sampling procedure, we would get a slightly different confidence interval. Sometimes it might be negative 6.5 to negative 4.2. Sometimes it might be negative 5 to negative 3. Sometimes it might be, negative 9 to negative, 1. It's going to be different every time depending on how we what kind of happens, this roll of the dice from doing this random sampling procedure. So each of those intervals is going to be slightly different. It's the procedure that we're talking about. And so if we did this 100 times, we would have 100 different intervals, and we would expect the true beta coefficient, so the true coefficient for weight, to fall within those intervals 95% of the time. So 95 out of 100 of those intervals will contain the truth. That's what a 95% confidence interval means. So it's not, these values in particular are not kind of what define this interval or how you would explain whether or not that true value is within these particular values. It has to do with the sampling procedure and the procedure used to calculate the confidence interval. So this is it's an important concept, and we're going to dive into this a little bit further in just a little bit, because I think it's really important to make sure we understand that concept. Okay, so the next question says, using the linear model you fit, calculate the p-value for the coefficient for weight. Interpret this value. What is the null hypothesis? What is the alternative hypothesis? Do you reject the null? So I'm going to use that same lm_empty_cars object, and I'm going to use the tidy function, and I get a p-value here. And so this p-value is very small. It's much less than 0.05. And so let's answer each of these different questions. And so first, let's state the null hypothesis. The null hypothesis is that beta 1 is equal to 0. And so written in words, the coefficient for weight is equal to 0. The alternative hypothesis is that beta 1 is not equal to 0. The coefficient for weight is not equal to 0. Let's name this chunk p-value. Did I name this chunk up here? I did. Good. Okay. All right. So we've got our null and alternative hypothesis. We need to interpret the p-value and then determine if we reject the null. And so the interpretation of this p-value is the probability of seeing a statistic as extreme or more extreme than, and what was the statistic we saw for weight? It's this negative 9.55. I'm going to round up to 5.6 since we've got a 9 there. At the negative 9.56, given the null hypothesis is true, so given that the coefficient for weight is equal to 0, so that probability is this tiny, tiny number, 1.29 e to the negative 10. Okay. So that is the interpretation of the p-value. So now we have to say if we reject. And because this is much smaller than 0.05, we reject the null hypothesis that the coefficient for weight is equal to 0 at the alpha equals 0.05 level. So this is all important. We want to say what hypothesis we reject, and we also want to say at what alpha level we reject it at. And so the alpha level corresponds to basically what cutoff we look at. And if the p-value is smaller than that cutoff, then we reject the null hypothesis. And if it's bigger than that cutoff, then we fail to reject the null hypothesis. This is important because in different contexts, you'll use different alpha levels. So alpha equals 0.05, that's the most common one for most kind of research that you'll see, or most statistical tests. But it's possible to choose a different alpha level, and there's certain contexts when people do. For example, in genetics research, this alpha value, the alpha value they consider significant, is really, really, really small. They might pick something like 1 times 10 to the negative 8th or something really tiny. And in that case, you would have to compare your p-value to that really small number and then determine if you reject the null hypothesis. And so it's always important to say what alpha level you're using when you reject the null. Okay. And here's the last part here. Using the model previously fit, pull out the F statistic and R squared using the glance function and interpret these values. I'm going to delete this code because we already did this at the top. Okay, so this is going to be the F stat and R squared. And so if you recall, in the slides, when we use the glance function, we can use this LMMT-cars, but we have to actually pull out the fit object. So if I just run this like this, it says no glance method for object of class _LM. So it doesn't work. I have to actually run this function on the fit object. And so if you notice, within this LMMT-cars object that I created, there's an object called level, one called spec, one called fit, one called pre-pros, and one called elapsed. So I want to run this function on the glance, or on the fit object. So I do it like that, and I get this nice output. And so the two things I'm interested in are the F statistic and R squared. And so let's interpret that F statistic first. It's right here, this 91.37. The F statistic is 91.37, 38 to round up. The p-value for this statistic is 1.29 times 10 to the negative 10. And so this F statistic is testing the same thing that our T statistic up here is testing, because we only had one coefficient in this model. And so it's comparing this F statistic. The null hypothesis is that beta 1 equals 0, and the alternative is that beta 1 is not equal to 0, because the F statistic is testing the full model against an intercept-only model. And so in this case, the full model includes just beta 1, and the intercept-only model contains just beta 0. Or, I'm sorry, the full model contains beta 0 and beta 1, and the intercept-only model contains just beta 0. And so for the model to be just beta 0, beta 1 must be equal to 0, which is why that's the null hypothesis. And so based on this p-value, we reject the null hypothesis that beta 1 equals 0 at the alpha equals 0.05 level. Okay, so that's the F statistic. Now let's interpret this R squared value. So the R squared value is 0.75. And what does R squared mean? So R squared describes the percent of the variability explained by the model. And so that means that 75% of the variability in miles per gallon can be explained by the model containing the weight of the car. All right, so now we've explained R squared and the F statistic. We've got our full application exercise. Let's knit it. And so there we have it. We've got, here's my knitted application exercise. Now I can save this and upload it to Canvas.